over to you, Paata, please.
Thank you, Joseph, for the introduction and for the invitation very much. It's my pleasure to give a talk in this seminar. Since the field the topology is a bit far, it took me some time to figure out what kind of topic I want to present, but eventually I decided the convex hull will be the most appropriate topic for this seminar. Okay, so I will be speaking about convex hulls of space curves. This is joint work with Jaume de Diospot and Jose Madrid. They are both from UCLA. One is a PhD student, another is a postdoc who got a job this year. So what's the question? So the question is the following. I give you a set, and the goal is to describe the convex hull. Now, we know the definition of the convex hull. It's a convex combination of all points. Sometimes it's a useful definition. You can work with it, but sometimes we want to have more explicit description of the convex hull. Can we, for example, if I give you a set, you take the convex hull, can you, for example, parameterize the boundary of the convex hull? Can you write the maps explicitly, something like this? This is not possible to solve problem in some generality, but if we assume some geometric assumptions you put on a set, let's say it's a curve and you know something about this curve, can you solve the problem in this case? Can you give explicit description of the boundary of the convex hull? Here is one example. In the plane, if you take a curve, let's say it's a graph of the function, then we know what is the convex hull. It's just what I draw on the picture. This is this red line. It's a convex hull, and you see it, and you easily understand that that's the boundary of the convex hull, and everything inside is points of the convex hull. Okay, let's take something a bit non-trivial example. Let's say that I have a curve in the space in 3D, and here it is. Let's see. Yes, here it is. It looks like this. Now the question is, what's the convex hull of the space curve, especially how the boundary of the convex hull looks like. Now, the answer is the following. So I will show you on the next slide. Upper boundary. So this convex hull, it will have kind of upper hull and lower hull. And first, I'm trying to show you upper hull. Upper hull will look like this. These are the straight line segments joining points like this. I'm not telling you at this moment how these straight line segments, how the endpoints of the straight line segments are chosen on the curve. They will satisfy a very certain equation, non-trivial equation. And the lower hull will consist, there will be a triangle kind of domain of linearity sitting from below, which will be maybe touching at this vertex, joining this point. And besides this, the lower hull will also contain this kind of straight line segments, joining this point with all points of this curve, joining, for example, this point with all points of the curve. And the same thing is happening from that side. Okay, 1 second. We are joining this point with all points of this curve. And that's the boundary of the convex hull. And everything inside is just the convex hull of the space curve. So it looks like this. Now, there are many questions one can ask here, for example, right? Why did we choose this triangle in such a way? Where did we pick the vertex, this vertex of the triangle? And what I said, that how do you parameterize the endpoints of these curves? For example, if you know what is this point, how do you find the second point? It's not necessarily true that it's parallel or, okay, picture here is very symmetric, but it's not absolutely clear how do you choose the second point. Okay. Now, before I go further, I want to give some simpler description, simpler way to think about this boundary. For example, let's erase the top, let's erase the upper hull, and let's look at the lower hull, that everything is kind of below the curve, lower boundary. And let's take it and project into this X and Y plane. then what you see is that this triangle will project here. And these chords that I draw, they will project in this, I think, blue lines that I draw it here. So here is the projection of the curve. Here is this segment goes there. And then what you see is this picture in the projection, we call it foliation. Foliation, what I'm saying is that once you know the foliation in this projection, you can easily recover the lower boundary of the convex hull. For example, if you know that projection looks like this, then the way you recover is that the graph, if you think that lower hull is a graph of the function, it is linear along this line segments that I draw along these blue lines. You know the value at this point, it just coincides with the curve. You know the value at this point, okay, let's say this point, it coincides with the curve, and the rest is just joined by linearity. So it's not difficult to see that if you see the foliation, then you can recover the lower hull of the convex hull of the space curve on this picture for this specific example. Now, foliations can be more complicated. For example, in this case, I'm showing you a curve. So here it is, and it ends here. Here is one endpoint, here is another. It's also in three-dimensional space. And okay, it's not the best picture, but it shows the following, that if you look at the upper hull, I'm not drawing the lower hull, like top of the space, convex hull, then it looks like this. So you join somehow by chords here. Then there is somewhere there is this triangle sitting. It's a like domain of linearity. It's a linear part of the upper hull. Then there are line segments here, line segments there. So they are also somehow chosen. And here is another triangle sitting. Then there are line segments there and line segments. This is only description of the upper boundary of the convex hull. And again, you can project this on the plane, and that's the picture you will see. In the projection, that's kind of the foliation. So sometimes it's difficult to look at the chords in the space, so it's easier to think about the projection. So the projection looks like this. And there are many questions. How do you find these vertices of the triangles? How do you find these points that I chosen? And the same thing about the chords. How do you find endpoints of the chords? So you see that picture becomes already complicated in three-dimensional space. In higher and my goal, as I said, will be to talk about in higher dimensions in Rn. Therefore, we have to make some assumptions so that we don't see some complicated pictures already in 3D. This I call complicated pictures. So one assumption that I will be making is that to avoid this kind of triangles and this kind of involved foliation, one assumption I will be okay, before I make that assumption, I want to say that the solution, finding convex half of space curves in 3D for some special case of curves, when determinant of the gamma prime, gamma double prime, and gamma triple prime changes sign finally many times, this problem was solved in joint works with my collaborators from St. Petersburg back in 8 years ago. And we found some algorithm which allows you to construct this kind of foliation, recover this foliation. It tells you where to find, how to find the vertices of the triangle, how to find these chords. It's a nice algorithm. There are some more assumptions needed on the curve, that the projection is a convex curve and it's strictly convex. And that's it consisted of 2 papers and one. And there was some algorithm found in that paper, and extending these results to higher dimensions is unlikely. I think it's not feasible. So I will be making some assumption on the curve when we can do something. And here is okay. Before I extend this result, let me say one more thing. That here is another picture I did with wire. So here is the curve, closed curve. And the convex hull, upper boundary of the convex hull looks like this. So what I was drawing here, if you see this triangle, it's exactly this triangle, not exactly, but it's something like this. So it is this triangle, there is linear part. If you ask how the lower hull looks like of this space curve, for example, what do you do with below? With bottom, so maybe you will kind of connect by chords like this, and then there will be one triangle sitting. It will be just joining these points. These kind of triangles in literature, sometimes they call it three tangent planes. Three tangent because they are tangent to the curve at 3 points. So you see the plane, the table, it is tangent to the curve at these 3 points. So this lower triangle, this triangle will be one of the part of the lower boundary, and then there will be chords here maybe, and here maybe, and that's essentially how would you construct the lower boundary, upper boundary, and everything inside would be the convex points of the convex hull. And as I said, we have some machinery how to find this in 3D, but we don't have anything at this moment what to do in higher dimensions. And the main question I want to talk to today is how the convex hull looks like in higher dimensions. And as I said, I want to make some assumption to avoid this kind of complicated foliations. And there is one case. Let's say I have a curve in 3D. And so here is a mistake. This should be that I have a curve which has 3 coordinates: gamma 1, gamma 2, gamma 3. And this is gamma 1 prime is positive. So this is 3 by 3 matrix. And what is written here, it's a mistake. It should be replaced by the first leading principal minor of this matrix. So if I would write, let's say that it's a vector, right? So I have gamma 1 prime. So let me gamma 1 prime, gamma 2 prime, gamma 3 prime, gamma 1 double prime, gamma 2 double prime, gamma 3 double prime, and there will be gamma 1 triple prime. So if I think about this 3 by 3 matrix, what I want to assume is that the first 3 leading principal minors are positive. So I'm assuming that this derivative is positive. I'm assuming that determinant of this matrix is positive, and I'm assuming that determinant of the whole matrix is positive. Let's make these assumptions on the curve. So that's what I wanted to write here. And if we make such an assumption, the first assumption, the fact that this is positive, it just says that the curve is kind of increasing. It's a monotone. It doesn't go back. The second assumption that this is positive, it says something about the curvature of the projection of the curve on the XY plane. And the third assumption is positive. It says that the torsion of the space curve is positive. And if we make these assumptions, then here is a very nice way to recover the boundary of the convex hull. Let's take a function which is a map from 0, 1 to 0, 1. So let's say this function has 2 arguments, lambda and x. These are real numbers. And it's a map. It goes like this. You take lambda times gamma x plus 1 minus lambda times gamma 1. Let's see what is this map. It takes, let's say this is gamma 1, and there is somewhere sitting gamma 0. So what you do, you take gamma 1 and take the convex combination with any point gamma x. So you just join this point, endpoint of the curve, with any point of the curve inside. So this endpoint is joined with any point of the curve. And then you do the same thing with other points. So what this map on the picture shows that you're just joining this endpoint to all points of the curve. And the claim is that what you get, this surface, it parameterizes this surface, which is exactly the upper hull of the convex hull of the space, upper boundary of the convex hull of the space curve.
Okay. So if gamma is algebraic, then so is the convex hull then, according to this upper hull.
If gamma is algebraic, it just means that so the way I understand is that gamma 1 is polynomial, gamma 2 is polynomial, and gamma 3 is polynomial, right? So then you want to make sure that this polynomial satisfy this strange assumption.
Yeah. So under these conditions, you get a semi-algebraic, or what is this upper hull?
Semi-algebraic, you mean the surface is also parameterized by algebra? Yes. Not always. No, not always. Okay. Not all. I think. Okay, I don't know. I have not done. I think not always, but I suspect that it's not. I was trying to solve. So it can be described as a sum. So what you are saying is that if we want to describe the surface as x1, x2, so let's say so x1, x2, phi of x1. So what I want to say now, I want to say that if we want to describe this surface as solution of this equation, right? Then phi is the algebraic polynomial. Is that what you are saying? That
yes,
algebraic?
Yes.
No, I think this is not true.
Okay.
So this gives you upper hull, but it gives you more information, not just that something is algebraic, it gives you explicit parameterization of the boundary of the convex hull, right? And the lower hull looks like this. You take the following map. You take map from 0, 1 cross 0, 1. Lambda and x are in 0, 1, and you take 1 minus lambda times gamma 0 plus lambda times gamma x. So what it does is that here is gamma 0, and then you join it with any point of gamma x. So you just draw these lines. That's the surface it parameterizes. What you get is that this is boundary, lower boundary of this convex hull of the space curve. So what you do is just you take this lower boundary, you take this upper boundary, you put them together, and this is the complete description of the boundary of the space curve in 3D. Okay, that's a very nice description, and the hope is that do we have something like this in higher dimensions? Maybe if we, it seems very natural to also consider this matrix with gamma 1, gamma 2, gamma n, and then put this, all the leading principal minors are put. Can we get something like this? And so it was a big surprise to me that there is a very nice answer, and I will try to show you this answer. So let's take a space curve in Rn+1. By some reason, I want to add one more coordinate. I understand that we are used to have gamma 1, gamma n from 0, 1 to R, but by some reason I want to add n+1 and think about it as a curve in n+1. I will explain this reason later. So we say that this curve has a totally positive torsion. This means the following. It means that all the leading principal minors of this matrix are positive, strictly positive on interval 0, 1. I showed you what it means in 3 by 3. In n+1 by n+1, it's absolutely the same thing. You just run through all the leading principal minors. Check that they have a positive sign. I have 0, 1, but it's not important. You can put any interval a, b by scaling. So for simplicity, let's write 0, 1. And here is one example, one instructive example to keep in mind. Let's say that my gamma t is t squared, t to the n, and g of t. Well, let's say the last coordinate n+1 is g of t. Then what it means that all the leading principal minors are positive. It's exactly equivalent to saying that n+1's derivative of g of t is positive on 0, 1. It's a checkable condition. It's maybe not very convenient condition to verify, but at least in this class of curves, you can see that it is equivalent to
This rules out moment curve because, I mean, for n.
Yes, it resolves the moment curve because if I take g of t equals t to the n plus 1,
yeah,
it's
but
exactly
but n needs to be odd or even, right, in this case?
There are results for moment curves, and for moment curves, there is a very nice paper of Carlin and Sharpley, and they gave a complete description of the convex hull for moment curve. And there are two different scenarios when n is even, when n is odd. Pictures look different. That's right. And we will cover that description in particular. Okay, we won't recover all the results, but questions about the boundary of the convex hull will be given. You're right. So we will be covering that example too. That will be one corollary. Yes. Okay, let's continue. So if you remember on the slides, I had this 0, 1 and 0, 1 in 3D. Now in higher dimensions, we'll need something more involved. So let's say we'll need the following simplices. So let's take DCL, delta CL, what it is. These are vectors, lambda 1, lambda L from RL. They are non-negative, and the sum is less or equal to 1. And I will need another simplex, delta star L, which is Y1, YL from RL, from L-dimensional Euclidean space, so that they satisfy this, they are in increasing order. 0 is less or equal Y1, is less or equal Y2, etc. is less or equal YL, is less or equal to 1. If I take L equals 1, then these are just intervals 0, 1 that I had in the previous slide. And
it's
here is
the Y chamber. The second simplex is called Y chamber, the representation theory.
Y chamber. Okay, that's I didn't know. I think I've seen some corner of the cube or something like this. Okay, here is the theorem 1. For any curve from 0, 1 to Rn plus 1 with totally positive torsion. So the leading principal minus are strictly, it's important they're strictly positive. If something is 0 at some point, then the statement is wrong. We have counterexamples. And assume, as you said, n is even at this moment. We have results when n is odd, but I will not write the statement when n is odd. It's a different conclusion because I won't be able to cover everything I want. So we have both n is even and odd, but in this talk I will be speaking when n is even. Let's consider the following map. You take delta CL cross delta star L. So these are these two functions. In L, when L was 1, it was just 0, 1 cross 0, 1. So you take a point from this cross product. So you take lambdas from here, and then you take x's from there. And then you map it to some j goes from 1 to L. So it's a convex combination of both. So it's lambda j times gamma xj plus this difference times gamma. It's a convex combination of endpoint gamma 1 with L points of the curve, where L is n divided by 2. Okay, so you look all possible, but you fix one endpoint, which is gamma 1, and then you take this point with convex combination with all points of the curve. But how many points? It's important that you take with points n over 2. The curve is itself is like, you should think 2L plus 1. And another map, it's analog of on the previous slide, you do the same thing, but you pick endpoint to be gamma 0. 1 point to be gamma 0, and then you take, okay, here is a typo, it should be L. And then you take the remaining points of the curve. The claim is, maybe it's difficult to say in higher dimensions what is top, what is bottom, but this should correspond to the upper hull, and this should correspond to the lower hull. And the claim is that the boundary of the convex hull of gamma 1 is the union of the surfaces of image of UN of the simplex union with Ln image of the simplex. This was exactly the case on this picture that I was showing. If I would just look at the image of this, it gives exactly this upper hull. If I look image of this, it gives you lower hull. That's the first theorem. Okay. And this is when n is even. When n is odd, the picture is different. It's not. It's not that you take the sum. You take some slightly different sum. Okay. Here is another theorem. So if you know parameterization of the boundary, so I will say a couple of words about these maps. They won't be. They are diffeomorphism. Okay. They are injective in the interior of this set, but they are not injective on the boundary. Something happens on the boundary of this set, but they are very nice in the interior of this set. So they're injective. So you can, for example, try to find the surface area of the boundary. There is a trick which allows you to also, if you know the parameterization of the boundary. It doesn't quite give you parameterization of the whole convex hull, but there is a trick which allows you to go inside the convex hull and parameterize the whole interior of the convex hull to construct actually a diffeomorphism. And that trick allows you to recover the volumes for the convex hull. So here is the theorem 2.
Can I ask a question on theorem 1? A very quick question.
Yes. Yes.
So, I mean, this map seems to be an affine map, is that right? UN and LN.
What kind of map?
Affine map on this product, on the simplices.
They are affine in lambda, but in X, they are not necessarily affine.
Okay, because gamma. Okay.
Gamma of X, gamma are not linear, yes. Yes, in lambda, they are very nice maps. You can calculate derivatives. So I will show you that when I will be computing volumes, there will be some simplification. But in Xi's, they are not. So here is the theorem. Now I will write with Rm because I don't see the reason to state with n+1. So it's a curve with totally positive torsion. If n is odd, okay, now I switched a bit. If n is odd, then the volume of the convex hull of gamma 0 equals, okay, here's the formula. It's minus, there is some -1 plus minus. You can ignore this if you just put the absolute value. It's divided by 1/2L factorial. You should think of it like n factorial. And then you integrate the following thing. So you take determinant of gamma x1 minus gamma 1, etc., gamma xl minus gamma 1. And then you put gamma prime x1, gamma prime xl, and then you integrate in x. X is the vector x1 xl over this simplex. Or, yes, over x1 xl, which satisfies this. So this is Lebesgue measure. You integrate, you get the formula for the volume, and then we have another one can get slightly different version of this formula. It's written here, so it's the same factor, but instead of subtracting gamma 1 in the first L coordinates, you subtract gamma 0, and then you integrate. The reason I'm showing you two formulas because I said that there was a trick to go inside the convex hull. And since I had two maps, there are two ways to go to inside. And that kind of tells you there are two different ways to obtain the formula for the volume. I don't see right now why these are equal, just if we forget about the whole geometry. Maybe there is some calculus argument. Okay, I thought about it, but I did not see that they are equal directly. But I can see it through the parameterization that I was showing you on the previous slide and the trick. Okay, here is the third theorem. Yeah, before I go to the third, it's a nice thing to have volumes because if you know we have now explicit formulas for volumes, you can try to prove some isoperimetric inequalities. Now everything is computable explicitly. Here is another formula for another theorem. So I have a curve 0, 1. It's Rn plus 1 valued with totally positive torsion. Again, n is even. then we can calculate the area of the surface of the convex hull. It is this integral. Again, you integrate always over those simplex, and there is this square root of determinant of SA transpose times SA times, it's a transpose of the matrix times SA and transpose. And what is this SA? So in one case, so here, I'm sorry, A should be 0, B should be 1. There is a typo. I was thinking that I have a curve on the interval AB, but since I'm writing everywhere 0, 1, so this should be 0. This should be 1. This is 0. This is 1. And here is what is this matrix SR. It's the same matrix I was writing in the volume, gamma x1 minus gamma r. So for 0, it would be minus gamma 0, gamma xl minus gamma 0, and then gamma primes. There is no r. So you take one such matrix with r equals 0, another with r equals 1, and you plug into this integral, and then you calculate this integral. I've never seen the areas of the surface areas of the convex hulls of space curves. So it looks like this wasn't known before, but there were some partial results about the volume.
Even for moment curves, it wasn't known?
For moment curves, okay, I have not seen that somebody calculated, because I think for moment curves, you can get these formulas for the area from the paper of Carrel and Charles, because I know that they did their everything. It's a very long paper, 90 pages. I read 80% of it, but I think you can get everything from that paper for moment curves. But they use what is called Vandermonde determinant. There is some nice formula, Vandermonde determinant, and that's the key tool they have. Okay, one of the key arguments, but for general curves, there is no this kind of Vandermonde determinant formula for general curves. Okay, let's go to the next slide. So this is theorem 4. It says the following. So I will show you several theorems, and they are essentially following by knowing this simple fact that you can explicitly parameterize the boundary. So if you take a curve in Rn plus 1 with totally positive torsion, then for any k between 1 and n plus 1, you can look at this equation, C naught plus C1 gamma 1t plus Ck gamma kt equals 0. You can consider this equation. You can ask how many roots does this equation have, different roots. And the claim is that if the curve has totally positive torsion, then this equation has at most k roots for any non-zero vector and for any k. So you should think maybe a good example to keep in mind is that we all know that if you would take a moment curve, so it would correspond to a polynomial, ck t to the k. We all know that polynomials have at most k roots. Definitely at most k real roots, but this is some kind of maybe extension. The key fact to look that this curve tk is satisfied is that this is totally positive. They have totally positive torsion. That's the key identity, a key assumption in this curve that makes them having at most k roots. Okay, now here is theorem 5. Let's take a curve from 0, 1 to Rn with totally positive torsion. It says the following, that so minimal number k points required to represent any point from the convex hull as a convex combination of k points of this curve is at most, okay, think about this like n over 2. You know, Karateadoris theorem says that if you have a curve in Rn, let's say, and then you look at its convex hull, then Karateadoris theorem tells that every point of the convex hull is a convex combination of at most n plus 1 points. But this theorem tells you that you actually need n over 2 points, essentially. There is integer part. This is integer part, lower floor function. But you should think for curves with totally positive torsion, it's a very strong assumption. Then you really need n over 2 points. You don't need n plus 1 point. So you can significantly improve that number. These kind of results were known for convex, what is called convex curves. And one way to get this theorem is to show that, so I'm not telling you what does it mean curve is convex in Rn, but there is some kind of natural extension of convexity in higher dimension case. And one way to get this theorem is to prove that the convex curves are curves with totally positive torsion are convex curves, and then you can get that statement from that known result, or you can actually get it directly using the parameterization. Okay. Now I want to talk about one more theorem. Let's see. What was the reason I had n plus 1 everywhere? I had this one more coordinate n plus 1. So the original reason we started looking at these convex hulls was this optimization problem. We started from the optimization problem. Suppose you want to maximize integral from 0 to 1 e to the f of x dx. Let's say you integrate with the Lebesgue measure. Overall function takes values between -1, 5. This is just an example. I just want to show you one of the motivations that we had. And then you fix integral from 0 to 1 f of x. Let's say it is 1. You fix integral of f squared. It can be different parameter, not necessarily f squared. And then you fix integral of cosine f of x. So you fix some functions of f. Your f, you should think of it as a test function. Can you find this solution? Can you say what is the supremum? And here is the theorem that what I want to say, that whenever you see this kind of question about maximizing some integral of some function, then you fix some other integrals, these questions, it's a folklore. These questions are related. They are actually equivalent to finding a convex hull of the space curve. In this case, it is t squared cosine t e to the t. You see t squared cosine t, they come what kind of composition sign with f. So what kind of parameters I fix, right? Cosine t, if you put instead of t f of x, that's essentially what you have here. And e to the is here. So the thing is that this optimization problem to find this supremum, it's the same thing as to describe the upper boundary, whatever that means. Okay, describe the boundary of the convex hull of the space curve. So now we have this description, so then we can just give explicit formulas for this optimization problem. So here is a general theorem in n dimension. Again, we have a curve in n plus 1 with totally positive torsion. And I need this notation of gamma bar equals gamma 1, etc., gamma n. So it is just projection onto the first n coordinates. And let's say that I have also last coordinates, n plus 1. Now, we want to solve the following optimization problem. We want to maximize integral from 0 to 1 of gamma n plus 1 composed with f. And we fix parameters. Gamma 1 of f is x1, gamma n of f is xn. And then we take supremum overall test functions from 0 to 1, bounded by 0 to 1. And as I said, that it corresponds to the boundary of the convex hull of a space curve. That's a folklore, but finding the boundary was not known, right? So if n is even, then this function here is the explicit formula. It's given in a parametric form. So you take lambda 0 times gamma prime of 1 plus sum j from n over 2, from 1 to n over 2. So lambda j times gamma bar xj. It's a point in Rn. So on this linear convex combination, value of the function equals lambda 0 times gamma n plus 1 at 1. So it equals this real number. So you just plug gamma n+1. And this is true for all lambda 0, lambda j from 0, 1, sum of lambda j equals 1, and for all xj's from 0, 1. I claim that this gives you a complete parameterization. It tells you values of this function at all points. This convex combination, they fill out the full domain of this function. These functions are given like this. So these are the solutions of this optimization problem. Under the assumption that gamma is positive definite, gamma has totally positive torsion. And we have similar results in when n is odd. But here I will only write when n is even. And one can also ask, if you, instead of supremum, you take infimum, then what do you get in this case? Infimum would correspond to lower boundary. Then you would just put here gamma 0 for infimum. So supremum gives you upper boundary, infimum gives you lower boundary, and the union of the graphs of these two functions is exactly boundary of the convex hull of gamma. Okay, here I want to show you one picture. Since it's a seminar, the title has geometry, so here is a very nice, should be an intuitive description of the convex hull in 4-dimensional space. So let's say that I have a curve from 0, 1 to R4 with totally positive torsion. Okay. And gamma is this curve, and gamma bar is the curve in R3. Now I showed you this function, right? M supremum, which parameterized the upper boundary of the convex hull in R4, which is a graph of the function of the upper boundary of the convex hull. So this function is given on the convex hull of gamma bar. Gamma bar is a curve in R3, so here it is. And here is one way to think about it. So I cannot draw you a picture in 4-dimensional space, but here is one way to think about this, this function. So what you do is, so this is in R3. Oops, sorry. This is in R3. And this is gamma bar. So it's a curve in R3. Let's take a convex hull of this curve in R3. Since gamma has totally positive torsion, gamma bar also has totally positive torsion. I claim that this convex hull you can fill out by triangle. So if you take this point, and then you just join by any point of the curve, you get one triangle. Then you join with another point, you get another triangle. These triangles, they don't overlap. They just overlap only along this edge. And these triangles, if you draw all these triangles, they fill out domain in R3. They exactly fill out the convex hull of gamma bar. So this is kind of, you foliate the convex hull of the gamma bar. And function M is defined on this convex hull. And it is defined like this. The function on each triangle, you know that the values correspond to the upper boundary of the convex hull in R4, right? On each this triangle, this M is linear function. It's just a linear function. The value here at this point, it equals gamma 4 of 1. Value at this point, it equals gamma 4. Gamma 4 is just the last coordinate of t, and the value is gamma 4 at 0. So you know the values at the end points, and the claim is that the function is linear. By linearity, you can recover all the values inside the triangle. And etc. You do in each triangle. So in each triangle, it is linear, but it's a different linear function. So that's how one can think about. Okay, that's how I can think about the upper boundary of the convex hull in R4 through these functions, which also solve this optimization problem. Okay, I guess I will stop here. I have still 3 more minutes.
Very good.
You have a lot of, plenty of time. Usually,
1 second. This is
take
50
as much as you want.
It's 50 minutes talk, right?
Yes, but so what time is it now? It's okay, so 50. Okay, you are very punctual. Okay. But okay.
Okay, maybe if you have some questions, I will answer these questions. Okay, I presented results. I was sometimes saying that n is even, n is odd, but we have for both even odd results in even dimensions. So it's interesting that the answers are different. I don't understand why. No, I understand now we have a paper, but still it's a bit of surprise that answers are changing depending on whether on the parity of the dimension. Okay, it's an interesting question to ask. What happens if I always had this assumption that the leading principal minors are positive, right? If one of the principal minors becomes zero, it just vanishes at one point, but it is positive on other points, then the conclusions are not do not hold of these theorems. Okay, maybe some of, but it's not true that the boundary is parameterized by this function un and ln that I was writing. That is wrong. So it's a very sensitive assumption, and I think that's the correct. This positivity of leading principal minus strict positivity is a correct assumption. That we have examples showing that if one minor vanishes, principal minor, then you don't recover the convex boundary of the convex hull. It's an interesting and open question to say what happens with these parameterizations when you assume that principal minors change sign. Like I had in the very beginning here, for example, in this picture, I will show you completely different variations because we were allowing these determinants to flip signs. And in this case, in this algorithm that we did in St. Petersburg back with my collaborators, we had this assumption of this determinant, the big determinant. Let's say that determinant of gamma 1 prime is positive, 2 by 2 leading principal minor is positive, and 3 by 3 changes sign finitely many times. Under this finitely many times, there is algorithm how to find the convex hull. I have no idea what would be the answer in higher dimensions when, let's say, the largest determinant changes sign finitely many times. I think the answer will be very complicated. But it still remains a big surprise to me that under the assumption that all determinants are strictly positive, answer is, I think, compact, clear, and not so complicated as in this case when determinant changes sign. Okay, so the question is if one can do something when determinants flip signs in higher dimensions. So this I don't know. Okay, thank you very much. If you have any questions, I'm happy to answer.